This is my best video to understand the concepts of
I've
kinematics.
seen maybe a prey. Powder moving somewhere there.
Let us enjoy the nature and learn.
Gonna come down, come down. In that direction.
Going there.
I am Anil Kumar.
What is trouble?
Welcome to my YouTube channel and the website Global Math Institute.
There.
This is one of my best videos on kinematics,
You see her?
where my passion of nature and mathematics comes together. We'll look into the horizontal plains of South African forest and we'll understand the kinematics, motion along straight line, in this particular video. The question is a popular question from previous test papers. However, I've given it a twist. Try to make it a bit interesting for my students. Position function of a leopard moving across a level ground in a straight line chasing after prey is given by s of t equals to t cube minus 15t square plus 63t, s in meters and t in seconds. Given this function of displacement, we'll understand all the concepts about kinematics, which include position, velocity, turning points, movement, direction, acceleration, graph analysis, speeding and slowing down, and total distance covered. That is all you need to understand to master this particular topic of kinematics. Now here's a very interesting situation which I witnessed, and these are the pictures taken by me. Let us try to understand the basic concepts which will form foundation for kinematics for all of us. So we'll begin with the position. Since the equation given to us is s of t equals to t cube minus 15t square plus 63t, represents the position of our hero leopard. So first thing first, let us just substitute some values for t and calculate the position s of t. So if I substitute 0, what do I get in this equation, which is t cube minus 15t square plus 63t, right? So substituting 0, we get 0 cube minus 15 times 0 square plus 63 times 0. So when you calculate, since we are just having 0 everywhere, it will be 0, and the coordinate point on the displacement line graph will be 0, 0. Is that clear to you, right? Simple as that. Now let's put 1 here, right? So we get 1 cube minus 15 times 1 plus 63 times 1, calculate the value. Let's put 3 here. 3 cube minus 15 times 3 plus 63 times 3, calculate this value. Then 5 cube minus 15 times 5 plus 63 times 5, calculate this value. Then 7, right? So we'll put 7 cube. See how simple it may become. Just substitute these values in the formula and then find the answer, right? 15 times 7 square this is, right? I've not been writing answers, so that's it, right? Plus 63 times 7. Calculate this value, and last 10 cube minus 15 times 10 square plus 63 times 10 equals to, correct? Now calculating these values, substitute kind of formula in your calculator, right, which I'm going to do. So we are having first as 1 cube minus 15 times, within brackets I'm writing 1 square, right? Bracket close. and then plus 63, and within brackets 1 equal to. So when I do that, I get a value which is 49. So we get a coordinate point 149. Is that clear to you? Now let's do 3. So I'm going to replace this 1 by 3 in my calculator, right? So practically, that is how you have to calculate these values. Do you get the idea? So I'm substituting 3 for 1 in the calculator, and I get a value which is 81. So we get 3 times 81 here. Now let's replace 3 with 5. So when I replace 3 with 5, what do I get? Okay. So one by one, we are doing that. It does take time. We get 65. So the value decreased, you see that? So at 5, we have 65. Now I'm substituting 7. But it doesn't really take a lot of time, right? And we get 49. So at 7, I again get 49. And at 10, let's do that. 10 cube minus 5 times 10 square plus 63 times 10. So you get 130. So at 10, we get a value of 130. So these are the different positions, correct? Now once we get the positions, we can kind of make a scatter plot here. We know t is greater than 0. So we are focusing on the first quadrant starting with 0. The last point is of course 10 for us, right? And the values here are 1, 3, 5, 7, 10. Let's say this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Let 10 be there, right? Okay. 10. So the maximum value 130. We can go by 20s here, right? So 20, 40, 60, 80, 100, 120, 130, right? So, okay, so those are the values. Maximum value we're getting at 10, which is kind of here. Now, 0 is the starting value. 1, we have 49. So we have 20, 40, 60. So 49 is at 1. So at 1, we have 49, which is kind of like here, right? Now at 3, we have 81. So 80. 381. At 5, 65. 1, 2, 3, 4, 5. 565. And then at 7, we have again 49. And at 10, we have 130. So what you see here is that we can connect these points and get an approximate graph. Do you see that? So that becomes the displacement with time. Time being in seconds and displacement in meters. Makes sense, right? So we have a scatter plot which kind of gives us an indication of the position of our leopard at different instances of time. Is that clear to you? Now, many things you can see here that the leopard is moving away from the starting point, right? But at this particular point, it kind of turns back, so moves towards you and then again moves away, right? So these are kind of critical points which we figure out. We are not sure exactly if these are the turning points or not. We are going to confirm that using what? Velocity function. Perfect. But anyway, with that diagram, you have understood how do we plot the position of our leopard, right? So we have visualized that particular thing with the help of the graph shown here, right? Okay, now let's move forward and do the second part, and that is we wanted to confirm the turning points, and these can be only confirmed if we find the derivative of the position function, right? So let's connect this velocity with the turning points. So how do you find the turning points? Well, the velocity is the derivative of displacement, correct? Displacement is given to us as t cube minus 15t square plus 63t. So we get derivative as applying the power rule 30t plus 63, correct? Now let's factor out 3. So we have t square minus 10t plus 21, correct? Now you could factor out this is t square, not t cube. Right. So that's a quadratic equation. We need 21 as the product sum of minus 10. So 7 and 3 can work for us, right? So it is t minus 3 times t minus 7. So from this equation, we know that the velocity function is 3 times t minus t and t minus 7. It's a quadratic equation, right? So if you visualize this, what do you get? Let's do that also. So, of course, when I put t equals to 0, then the velocity is 63, right? So let's say this is 63. This is at t equals to 0. We're trying to figure out the velocity function. Now it has two zeros, one at 3, the other one at minus 7, right? So I'm just making approximate graph here. So it will come down and hit and then go back, correct? Do you see that part? So from this equation, without doing much calculations, we figure out that velocity will be 0 at time 3 and at 7, correct? This is, we are writing time in seconds, correct? So we get our graph. From the graph, it is absolutely clear that the velocity is 0 at 3 and 7. So that means, so since we have velocity equals to 0 at t equals to 3 and 7, s of t, that is the displacement function, has turning points at t equals to 3 and 7. You get the idea. So let's confirm. Let's go back to our position vector, position equation. And what do we see? We do see that at 3 and 7, we do have these turning positions, correct? So I'm highlighting the values. So 81 at 3 and 49 at 7, correct? Those are the positions, perfect. So you see how we have connected the velocity with the turning points of the leopard, right? So that after 3 seconds and after 7 seconds, leopard turns. It really means that up to 3 seconds, the leopard was going away, right? Do you see in this portion? The leopard was going away. And then from here to here, it is returning, right? Or approaching. Do you see that? And then again, it goes away. So these turning points also give you an idea during which duration is the leopard going away from its starting point, the point of reference, or going towards it. Is that okay? So we can combine these two things, displacement and velocity graph, and get that information, right?
After attending university. The winner of this year's Certificate of Achievement Schulich Leader Award is Akshi Kandivani.
Great. Our student, Akshit, gets highest marks and the most prestigious Schulich Leader Award. You can be there. Join our classes and excel. So what we learned just now is the direction of movement, right? Going away and approaching. We found that displacement t cube minus 15t square plus 63t, when you differentiate with respect to time, you get velocity, which is 0 at 3 and 7. So there are turning points at 3 and 7. And now, let us summarize. How do we find the direction of movement going away and approaching? You see that? So we saw in this particular case, very important thing, and that is, if you look at the position vector s of t, right? It is always positive. Do you see that? It is always positive. It is always positive. All throughout, all the values which you found, they were all positive. But if you look at the velocity vector, I should say velocity function, then we found that it has zeros at 2 points. One was at 3 and the other one was at 7, right? This is positive from 0 to 3, negative and then positive, correct? So let me rewrite this to be our starting point 0. The reference point. So we call this as the reference. So from the reference position, when time t was 3 seconds, velocity was 0, but before that it was positive. So if we have positive and positive, then we can say that our leopard is going away. But when the signs are different, as in the second phase 3 to 7, then it is approaching. So whenever the velocity and displacement signs are same, then it is going away. You get the idea. So we can summarize that if the product of displacement with that of velocity is greater than 0, then it means away. But if the product of displacement with velocity is less than 0, means approaching, coming closer to the reference point, the starting point. You get the idea. Whatever you take as the reference point. Here origin was our reference point. So that is a very important summary from this particular learning. Correct? Make a note of this. Now let's move forward and see the next parameter, which is acceleration. As you know, acceleration is derivative of velocity. So let's differentiate the velocity function and find the acceleration, right? So how do you find acceleration? Acceleration with respect to time is derivative of velocity. Velocity is 3t squared minus 30t plus 63. We get 6t minus 30t, right? You can here factor 6 and you get t minus 5. Perfect. So we see acceleration is 0 at 5, correct? So let's try to analyze acceleration, right, on this graph. So we notice that acceleration is negative if t is less than 5, right, but positive after that. So we can draw this graph where this value is t equals to 5, right? And of course, when I put this as 0, I get minus 30. And that is the acceleration whose units are meters per second square. Is that okay? Minus 30 meters per second square. And then it is 0 at 5. At 10, it will be plus 30, right? So if I extend it to 10, I'll get this point at, I can write this as 10 as 30, right? Meters per second square is going to be the acceleration. Now the important thing here is that the acceleration is negative, right, from 0 to 5 and then positive after that. Now from this function of acceleration, we can actually figure out a very important criteria, and that is speeding and slowing down. Now for speeding and slowing down, what we need to do is that we have to look into acceleration and the other important function, which is velocity. So we have to look into both. Because if the velocity and acceleration are in the same direction and going positive, then it is speeding, right? But if they're opposing each other, then it is slowing down, correct? Now, on the same graph, if I want to write velocity, then I know velocity graph was 0 at 3 and 7. So velocity was kind of like this, right? So better I use a different color. Okay. Let me use a different color for acceleration. So, okay, I'll use this color for acceleration. So, as you can see, from before, we have got three different intervals, right? This is when velocity is 0, 3 and 7, right? So, what do you notice here? So, if you are looking into speeding, so when is that speeding takes place? It is when the product of acceleration and velocity is greater than 0. Do you see that? And slowing down happens when the product of acceleration and velocity is less than 0. So in this particular diagram, we could summarize speeding and slowing down as looking at these intervals from 0 to 3, 3 to 5, 5 to 7, and thereafter. So if you see 0 to 3, the signs are opposite, right? Since acceleration is negative but velocity is positive, so it is slowing down, right? But then both are negative, so it is speeding, correct? And then we have opposite signs once again, so it is slow, and then it speeds. You get an idea, right? So from the combination of these two graphs, we can figure out when is the object speeding and when is it slowing down. And clearly it is speeding when they have the same sign. And they have the same sign between 3 to 5 and after 5, right? So this is from 3 to 5 and then from after 10, right? So 10 onwards. Sorry, 7 to 10. Because our interval is only till 7 to 10, till 10, correct? And slowing down from 0 to 3 and then from 5 to 7. You get the idea. So we can actually figure out when is our leopard slowing down and when is the leopard speeding when we consider velocity and acceleration functions, right? So I'd like you to summarize this speeding and slowing down learning here. So we just learned that speeding takes place when the product of acceleration and that of velocity is greater than 0. And slowing takes place when the product of acceleration and velocity is less than 0. Clear? And from the graph, we did figure out that initially it was slowing down from 0 to 3. And then from 3 to 5, both were negative. And then from 5 to 7, slowing down again. And then from 7 to 10, it was speeding. You get the idea, right? So that is how you can summarize after you find that the acceleration was given to us as 6t minus 30, which was 6 comma t minus 5, correct? Using these three functions, correct? So with that, you have understood displacement, velocity, and acceleration functions as well as their graphs and how are they related. So now, I'd like you to analyze the situation when all the three graphs are given to us together. So now we have this particular graph. Can you recognize which one is velocity, which one is acceleration, and what is the displacement graph given to us, right? So clearly from here, the cubic function is your displacement graph, right? And the blue one represents the velocity. with time, and green is the acceleration with time, correct? I like you to mark what are the intervals where it is moving away. Can you write down? Moving away means that both displacement and velocity have same sign, right? So displacement is always positive, so up to this point, which is 0 to 3. Both are positive, and after 7, right, is moving away, correct? When is the leopard approaching, meaning moving towards, it is between 3 and 5, right? When is the leopard speeding? When is the leopard slowing down? Speeding when both acceleration and velocity are in the same signs, right? So which is 3 to 5 and from 7 to 10. Slowing down initially, both are positive and negative. So 0 to 3 and then 5 to 7. Is that clear to you, right? So that's the summary of our learning, which we can get from the equations graph is shown here, right? All of them together. This is a very important question. It is asked so many times in different ways. Now, lastly, let us also consider the motion. So till now, we have analyzed the situation, made a graph, and then figured out when is the object going away, when is it approaching, when it's speeding, and when it is slowing down. Now let's look into a one-dimensional motion along a straight line. We call this as a motion graph. So now, from the given situation of position and velocity, velocity is kind of important to consider since it gives you the turning point, right? So what I've done here is taken up the position graph from 0 to 5, and from this 2D graph, this is a 2D graph, right? Giving us displacement versus time. We are going to draw motion along a straight line, right? So when we look into this motion along a straight line, we have a reference point O. Displacement is position from the reference point O, right? So at t equals to 0, our displacement s is also 0. So what is happening here? This is 0. The object moves in forward direction for the first 3 seconds, and the maximum distance covered is 81. So the object goes, let me draw it in a different color, it looks nice, right? Up to this point. Here, time t is 3 seconds and the displacement is 81 meters. Now at this instance of time, leopard changes direction, and from 3 to 5 it is approaching, right? So for these 4 seconds, and comes down to a place where the distance from the starting point, or we should say displacement, is I think 41 or 49. Let's check. We calculate this as 49. Okay. So it was 49. So 49. So it comes back. Let's use a different color. Let's up to here. So that position is at t equals to 7 and the displacement is 49. Is that clear to you? Now at 7 it again turns. It again turns and goes in forward direction and reaches somewhere here, which is at t equals to 10 net displacement. Distance from the reference point O is 130, right? That was the maximum distance. Do you see that? So this is what we call as the motion graph. So along a line, we have shown the displacement of the object, which is leopard in our case. Is this concept clear to you? Perfect. So at each turning point, it's a good idea to write down the displacement, right? Now this also gives us information about the distance traveled. So we know the positions, which is the displacement, and now let us see how do we calculate the distance traveled, okay? Now distance is always positive. So we first add from 0 to 81, so that is 81 plus. We'll add this distance. How much is this distance? This distance is 49 minus 81, right? Absolute value of 49 minus 81. The amount of distance it turned back, and then from 49 to 130, so we'll also add absolute value of 130 minus 49. Is that clear to you? So that is how we are going to add all the displacements within the intervals when the object is moving in one direction. And positive values of their addition will give us total distance, right? So we have 81 plus, we have to add 81 minus 49. I'm doing these calculations with you so that you get the confidence that you can also do it, right? 130 minus 49. And what we get is 194. Do you see that? So we calculate the whole distance as sum of all these, right? So we add it from here to here, then this, and then this, all the three. When you add individually these absolute values, you get the total distance traveled. And the units, of course, are in meters. So the leopard in this chase traveled a total distance of 194 meters. Make sense? So I hope this has brought you a lot of learnings. It's a good idea to now capture the learnings, correct? So this is the last screen. I'd like you to pause the video and write down what did you learn from the whole exercise. So we learned that the derivative of position is velocity and derivative of velocity is acceleration. They are all linked, right? We can actually get a lot of information from these. One, if velocity is equal to 0, then it implies that there could be a turning point. Sometimes it is not, we could have a x cube type of a function. Now, second thing, so that turning point gives you whether it turns or goes in which direction, right? But actually approaching and going away is found from the product of displacement and velocity. If this is greater than 0, that means it is going away. And if this product is less than 0, that means approaching. That means coming closer, right? The other important product is velocity times acceleration. If that is positive, it means speeding. And if this product of velocity with acceleration is negative, that means slowing down. And from the graph, you can easily see when is one positive, when is one negative, and then figure out the intervals where the object could be speeding or slowing down. Make sense? So I hope with this, you get complete information of kinematics and how do we solve questions related to kinematics, especially when we're looking into horizontal planes along straight lines. Enjoy our video, The Chase of Leopard. The next coming up is to look into acceleration, right? So we'll look into the concepts of acceleration and have some very beautiful questions there. So I hope with that you understand and appreciate the whole exercise. I hope you understand the concepts of kinematics. Feel free to share your comments and suggestions. If you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.